click. Yeah, now we are being recorded. For starters, my apologies because today's lecture is going to be extremely boring. I was bored to death preparing it, so I don't envy you, but it's at least very short today. And I have to do it because I have to tidy up some mess which I made in my previous lectures. I am partially guilty for doing this because I was misled by the book, this blue book, the Bible of Path Algebras. You know, I believe that in mathematics, it's extremely important that you prove your claims in the most economical ways. So use as few assumptions as possible, and your tools are as clear as possible. And all right, I'm reading some literature. I see people make some claims. Okay, they are sensible, they are interesting. I write them down, I teach them to you, and then I realize, wait a second, but these claims are far more general. You can use the same arguments without basically no assumptions which they use in the books. And this irritates me. I have to go back and somehow clean it up. And this is what we're going to do today. In particular, for what I want to explain to begin with is that in fact, the path algebra for absolutely any graph, you can think about crazy graphs with uncountably many vertices, edges, whatnots. Nothing has to be finite whatsoever or even countable. And everything works, and every path algebra is always some sort of a matrix algebra, okay? So this is not the big surprise, but then when we study examples, we often get some sort of subalgebras of matrix algebras. There is a reason for it, because in full generality, we can prove a certain isomorphism claim without assuming anything whatsoever about our graph. So this is what I want to begin with. This means that I have to go back to a definition which I showed you in the previous semester. And this is a definition of a matrix. Well, you might think that you know what matrix is, especially if you've seen the movie. But I'm very serious here. I really want to have the matrix in its full generality. So for me, a matrix is something gigantic. I take arbitrary sets I and j, and I take R to be a semi-ring. And for me, the R valued I cross J matrix is a map, arbitrary map from the Cartesian product A cross J into my semi-ring R. Okay, this is what a matrix is. Okay, it has two legs, it has two indices, but there is nothing more you have to assume. All right. Then you can define the transpose. We don't need it right now, but what we need, it's very important. We need the concept of the elementary matrix. And again, we have it in full generality. So for any pair of indices Mn in I cross J, we define the elementary matrix Mn by the formula, which is just double conic cross delta. So this is something which has 1 in the nth row, an nth column, and 0 everywhere else. Okay, and then you have a very easy multiplication rule for elementary matrices, and everything works beautifully as in the finite case, and that's all we need to prove our theorems. Now it's obvious that we say that the matrix is square if I is equal to J. And I remember I was thinking, does it have to be equal, or should we take it bijective? You know, these are just sets. After all, you can have, say, I to be natural numbers and J to be rational numbers. This is just countable infinity. So there is an isomorphism, or if you want bijection, add between them. But then it turned out that it causes more trouble than it's needed, and it doesn't give you anything more. So I just assumed that square really means that the sets are equal. So there is a canonical identification between them, if you want. Okay, and so we need to know what the square matrix is, and then we need another thing. How can we multiply matrices? There is a concept of being row finite and column finite. This is a very obvious concept, so maybe I will unclick this one and now highlight that one. Yes? Okay. But you should use a mic when you speak. Yeah. Type on the definition of a transpose.
Yes, I think the domain should be J times I.
Oh, yes, of course. You're absolutely right. Yes. Yes, of course.
It does not make sense.
Yeah, of course. Yeah, thank you so much. I'll correct it later on. this is very good. And okay, but now let's go back to defining what it means to be row finite and column finite. The definition is obvious. It means that when you look at the row of a matrix, there are only finitely, when you fix the row, a row of a matrix, then there are only finitely many non-zero entries in this particular row. It doesn't mean that the row cannot grow in its length to infinity, right? In the first row, you might have 2 million non-zero entries, in the second 20 million, and you can go to infinity. So it doesn't mean that this is a finitely supported matrix, okay? And likewise, you define a column finite, and you fix a column, and in your fixed column, you have only finitely many non-zero entries. And using symbols, this is what is written here in this yellow highlight, all right? So you fix an I, it's arbitrary but fixed, and then when you take the set of all Pij's, where J runs the whole, possibly extremely huge set J, then there are only finitely many guys that are non-zero. And the same for the column, okay? And then you see that the upshot is that if you have one of the matrices row finite or column finite, then you can multiply them. And now I'm looking where I have this formula. I mean, that's the obvious formula. Yes. Yes, so the claim is that if so what I have P an IJ matrix and Q a JK matrix, and I want to multiply them, and either if P is row finite or Q is column finite, it suffices that one of them satisfies such a condition. But it has to be that the matrix which is on the right must be column finite if it is to work for arbitrary P, and the matrix which is to the left must be row finite if it is to work for arbitrary Q. All right, and if P is row finite or Q is column finite, then you can multiply them, and that's the obvious multiplication formula. Just as you remember from kindergarten, that's exactly the same formula. And it makes perfect sense precisely because of these conditions, right? Because of these finiteness assumptions, that sum, although seemingly infinite, because J can be as huge as you want, because of this finite support, this is always a finite sum. Okay, so it makes perfect sense. Okay, and so this is what we did in the previous semester, basically. But now I added a proposition about considering square matrices that are both row and column finite. Okay, so I want them both to be row and column finite, so that I can always multiply them from any side. Okay, I can take any pair of matrices and in any order, and I can multiply. If you have all of them row and column finite. Okay, and what do I claim? I introduce the notation MIR. I take all maps from I cross I into R, so that's an arbitrary matrix. But now, as I said, I demand M to be both row and column finite, and that set I denote as MIR, and I claim that then MIR is a semi-ring with respect to the pointwise addition and matrix multiplication which I introduced earlier. Furthermore, if R happens to be an algebra over some field K, then this MIA is also an algebra over K with respect to the pointwise vector space structure. So when we're talking about semi-rings, then we only looked at addition, so that's a structure of an abelian subgroup. But now when we're talking an algebra, yes, I want to talk vector spaces. And when I have maps from some set into a vector space, obviously the space of all maps is with respect to pointwise addition and pointwise scalar multiplications again a vector space. Okay, so in this sense it's obvious what I'm talking about, what I mean the vector space structure. But well, I claim that now when you take this matrix multiplication defined earlier, then you have an associated bilinear product. Okay. And this will be an exercise for somebody to do. I skipped the proof because it's something that should have been done in the previous semester, but that's what I need right now. So I had to highlight it for you. Yeah, that's I forgot to highlight it. So please bear it in mind, and I'll ask somebody in the recitation class to prove it for the next week. Okay. And I think that's all I need from this total recall. So I can kill it now. No, don't save changes. I don't need Dropbox anymore for the time being. What close window? I think I have to stop sharing and now start sharing again, but now with my whiteboard. There we go. Okay. It takes a while to tidy things up. Okay. Let me clear all drawings. All right, then I can grab my pen and start my lecture. I don't know why these random things appear. I'm not doing anything and I have this stuff. Okay, so let E be any graph, as crazy as you want. Now, when I look at its path algebra, then it always decomposes in the following way. I have a direct sum over all pairs of indices. So let's call it VW. They run P0 squared. And here you have chi V times the path algebra and chi W from the right. We did it before in the finite case, but it has nothing to do with the finite case. There are no assumptions necessary, right? This composition is obvious because the path algebra is a linear span of finite paths, okay? And every finite path starts and begins somewhere. So it's clear that a finite linear combination of elements from this direct sum will give you any element in path algebra, and vice versa. This decomposition is unique because you cannot have a path which is simultaneously in chi v, ke, chi w, and chi v prime, chi w prime when v w is different from v prime w prime. Then we have that the intersection of chi v, chi e, chi w intersection with chi v prime, ke, chi w prime. This is 0. Okay, that's completely clear. Because if you take if you want to be very pedantic, if you take an element which belongs to both of them, well, and then this pair is different. So either V is different from V prime or W is different from W prime. So you can multiply it. So for the sake of simplicity, to focus attention, actually say that it's V, which is different from V prime. Then you take a path, say some element of one set, and you multiply it by chi V. It should change nothing because it's in chi V, chi W sector. Then you multiply it by chi V prime, chi W prime. Again, it should change nothing because it's also in this V prime, W prime sector. But then you just multiplied chi V and chi V prime, which is 0. So that's like an obvious argument. I don't do any formal proof here because it's really, really clear that you do have this decomposition. So let me erase that stuff. And it holds always in full generality. And it's something which allows us to view any path algebra as a matrix algebra. So this is what I want to prove, that any path algebra is a kind of matrix algebra. So now I want to define finitely supported square matrices. So these are, oops, I cannot write with an eraser. So finitely supported square matrices. Okay, I call it ME. If you think there should be better notation, let me know. And this stands for the following. I'm taking all elements of finitely supported maps from, sorry, this is not I, now this is E0, E0 cross E0, but with values in the path algebra, surprise, surprise. But now, and this will be another exercise for the recitation class, because I have finitely supported, let me write it down on this page. For any set and any vector space, so this is any set and this is any vector space. All right, because I'm finitely supported, I can write this vector space as canonically isomorphic to finitely supported maps from X into the field. Tensor product, of course, over K with W. Oops, well, what am I writing? WV. So this will be, I also asked somebody today to prepare it, the proof of it for the next recitation class. So this is a general fact. In our case, V is the path algebra, viewed as a vector space, and X is E0 cross E0. So this is a general fact that you should bear in mind, and it somehow streamlines the notation. So I can just write it down if you want as map E0 squared K tensor product KE. But mind you, you can do it only for finitely supported maps. Okay, so that's what I'm taking here. And I am, and here I write the following extremely crucial condition. Because, you know, in a way you can say that, well, it's completely trivial to say that an algebra is a subalgebra of a matrix algebra over the same algebra. Just take the diagonal times the algebra. That's not the point here. This would be completely useless and trivial. The point here is that when I take this ME, I'm taking only such matrices that have the property that M of VW, guess what, is an element of chi V, KE, by W. Okay, and I'm going to convince you that this is an algebra which is actually isomorphic to the path algebra. Yeah. So the upshot is that now what we're really talking about, we are talking about some sort of a subalgebra of a matrix algebra, but the subalgebra is carved out in a very particular way. It's what we study is really these spaces of paths from a vertex V to a vertex W. But that's the structure of the graph. That's what we see in the adjacency matrix and so on. So that's why when it comes to concrete examples, there's no surprise when we say, oh, well, for instance, all these spaces are one-dimensional, so that's just putting a field. At some other places you have always zero, and all of a sudden you get some concrete subalgebra of a matrix algebra, not even over a field. Okay, but in general, I have to make sense, I have to put here this path algebra KE. Yeah, but that's non-trivial precisely because of this condition, this thing. Okay, so now that's just a construction, and now I want to prove that everything holds water, that it makes sense. Let me skip this page. Okay, so now note the following, that since elements, oh, Jacek, you promised me that I'll get used to it. I'm still not used to it. Since all elements of ME are finitely supported, they are all both row and column finite. So actually, having something finitely supported is much stronger than having something row and column finite. Let me go back to this place. So imagine that this is my infinite matrix. And when I say that I'm finitely supported, well, when there is some area and only here I have non-zero entries, everywhere I have zero entries. Okay, it's kind of like building this M infinity algebra. Remember? You have an arbitrary size algebra, but every element is a finite size. Okay, but when I say row and column finite, I'm sort of having a zone in my matrix. Roughly speaking, you know, I draw the upper line, I draw the lower line, diagonals inside always, and I demand that things outside of the zone are zero, but inside the zone there can be anything. So in particular, I can be non-zero in every entry in the diagonal. Okay, an infinite diagonal matrix is always row and column finite because there's only one non-zero element in each row and each column. Okay, so you can think about row and column finite matrices as matrices with some very thick and strange diagonal. Right? I mean, these curves can change as they want, but all they stand for is that in every column I have finitely many non-zero entries and the same in the row. So this gives me that picture. So that's something far more general than being finitely supported. But I want to do this level of generality because this is all I need to have this matrix algebra. This is all I need to have be able to multiply matrices. I don't need them to be finitely supported. Obviously, if you take two diagonal matrices that are as infinite as you please, you can multiply them. Okay. So now we have it explained. So I'm taking something smaller, but in particular, I can now claim that ME is a subset of this matrix algebra M, and not to screw the notation, E0 as the set of indices. And here I have KE, right? This is what I defined at the beginning when I was making the total recall from the previous semester, right? Remember that here was an arbitrary algebra and there's a proposition that says that if I take all matrices that are both row and column finite with values in some algebra, I have a matrix algebra. So this ME, because it's by definition all matrices that are finitely supported, they're both row and column finite, so I have a subset of an algebra. Now it's clearly with respect to the pointwise structure, the pointwise vector space structure, ME is obviously a subspace of ME0 KE. Right, this is a no-brainer. So now what I want to show is that the matrix multiplication restricts to ME. And what I mean by restricts to ME, well, of course, I can always restrict the domain. I can take ME cross ME and multiply. Well, these are vector spaces. I can even take the tensor product. But the point is where it lands. I want to, by construction, it lands in M0 KE. But I want to prove, why do I have Avast right now? My God. But I want to prove that in fact it lands in something smaller, notably in ME. And then I'm done, because then I have that ME is a subalgebra of the matrix algebra M0 KE. And then it remains to show that this is that ME is isomorphic as an algebra with the path algebra. Okay, so this is the name of the game right now. I want to prove that I can restrict the matrix multiplication in the matrix algebra M is 0 KE to ME. So for starters, I love that phrase. For starters. Maybe I should, yeah, recall. No, yeah, I showed you matrix multiplication. You know how it looks like. So for starters, M times N. Well, maybe I'll write it down. So M times N, well, is finitely supported again. Right, because if I take Mn of VW, then it's a sum over U in E0 of M VU N UW, okay? And now because M and N are finitely supported, it means there are only finitely many V's where M doesn't vanish and only finitely many W's where N doesn't vanish. So this means that there are only finitely many pairs VW where Mn doesn't vanish, okay? Because if I sum zeros, I still get a zero. So for starters, we realize that when I multiply two matrices that are finitely supported, I get again a matrix which is finitely supported. Okay, but moreover, I have to check this crucial condition, that's this essential condition, okay? This is what I have to check. So let's do it. I take any matrix, any vertex U, and I see what happens with the multiplication. I have M V U times N UW. Okay, then I'm summing up over U, but in particular, let's fix an arbitrary U. And then note that this is an element in what? Chi V, KE, Chi U, Chi U, KE, Chi W, okay? But obviously, this is inside, it's contained inside Chi V, KE, Chi W, right? Because I'm just taking all paths from V to W that factor via U, but in particular, they are paths from V to W, okay? So I have this containment, and of course, it's a vector subspace. So when I sum over such things, I don't leave this vector space. So this means that I can indeed restrict, yeah. Therefore, the matrix multiplication restricts to ME. So ME is a subalgebra of the matrix algebra M is 0. Okay. And for all of you who are somehow familiar with non-commutative geometry and remember the Gelfand transform, remember taking subalgebras in C-star algebras corresponds to taking quotients of spaces. And when you look at the classical topology, when do you get something non-trivial out of something trivial? Precisely by taking quotients, right? You take some spaces which are very regular, and then I don't know, quotient by the fundamental group, and then you get some non-trivial manifold. Okay, so this is a general recipe. So don't think that taking a subalgebra is a trivial procedure. It is not. No, It's taking a quotient, which is easier because taking a quotient corresponds to taking a subspace. Of course, you can take a crazy subspace inside the space. I don't know. You can take a Riemann surface out of the Euclidean space. One is trivial, one is not trivial. So I'm not saying that quotients are trivial, but somehow you might have a tendency to think, well, it's just a subalgebra, so it has the same properties as the algebra. No, this is completely wrong. And Jacek can correct me if I'm wrong, but I think with a very beautiful and important property of nuclearity in sister algebras, there is some theorem, I believe, that at least when you are not in type 1 sister algebras, if you are beyond type 1, then in any nuclear sister algebra, you have a sister subalgebra which is not nuclear. So this is completely crazy. I mean, this is like as far from being hereditary as you can. And this is a very beautiful theorem, and nuclearity is something absolutely crucial. It's in the real life examples that you need, you are usually nuclear, okay? But this is not the property which is easy to check. There are zillions of equivalent formulations, but that's one of the functional analytic subtleties of sister algebras. And it's very desirable to know that your sister algebra is nuclear if it is indeed nuclear. But that's a property which you know, it's not so easy to establish just by knowing that your subalgebra is carved out of some bigger algebra. You know nothing. You just have to prove it from scratch. Okay, this is just a remark about the non-triviality of this construction. I want you to get some respect for ME. It looks kind of innocuous, but it is non-trivial. Well, and the proof of a cake is in the eating. So let's prove that ME is isomorphic to KE. Okay, this is what I want to prove, that the isomorphic is algebras. So finally, note that the obvious assignment assignment, which does what? I take my path algebra here. I take its basis element chi p. I map it to f of chi p. So let me denote this map by f. And well, that's basically what we all did before. So I apologize for doing it again, but we did this calculation before. But this was so stupid to assume so many things, that it's finite, acyclic, and all that nonsense. None of this is needed. This is a completely general calculation. That's why I have to redo it. But I was misled by a book, at least this is my excuse. Okay, so what it is? Well, obviously, I'm writing it down as an elementary matrix. ESP P, tensor product chi p. Okay, and I can do it because of this property here. You see, this is not true when I take the matrix algebra, full matrix algebra, because I'm not talking finitely supported functions. So then, well, it would be some sort of a tensor product, but you would need to take some completion of a tensor product. It would not be an algebraic tensor product. Here, this is an honest algebraic tensor product. So that's why I can write these elements in this tensor product form, which is very convenient. Okay. And of course, this is an element in my ME. Right, this is clear. Well, it's obviously finitely supported, and it obviously has the property that that defines ME. Notably, that in the slot labeled by SPTP, I have chi of a path. I have some finite linear combinations of chi's of paths that begin in SP and end in TP, and obviously P begins in SP and ends in TP. Okay. And this assignment is obviously a vector space isomorphism. That's because I'm mapping basis to a basis. But that's because of this decomposition. You see? So this decomposition guarantees that the map which I wrote is a vector space isomorphism. Yeah, because when you look at the matrix, the matrix algebra, subalgebra ME as a vector space, that's exactly a direct sum of vector spaces over all slots. But that's the same direct sum. And my map is basically tautological. I'm just relabeling things and show that my relabeling is consistent with the multiplication. So it remains to show that F is an algebra homomorphism. Okay, but this is easy to do. Maybe I'll do it on the next page to have it all calculations on one page. So I take f of chi p times f of chi q. This is obviously E SP TP tensor with chi p. And here likewise, just I replace P with Q. Okay, this is a tensor algebra, so I multiply component-wise. And when I multiply the two elementary matrices, I have the usual law of multiplication of elementary matrices. I have a Kroneker's delta between TP and SQ. And then I get the elementary matrix where now the first entry is SP and the last entry is TQ. And on the other leg, I have chi p times chi q. Okay, so here I just multiply matrices and here I multiply in my path algebra. Okay, so far so good. But now, note that, well, of course, when TP is different from SQ, that's just all zero, it vanishes, it's not there. But if TP is equal to SQ, then the paths P and Q compose because the end of P is the beginning of Q. All right. And when they compose, I can rewrite it in the following way. I keep this Kroneker's delta. Oops, of course. TPSQ. But now, because the path PQ exists when TP is equal to SQ, well, of course, the beginning of a path P is the same as the beginning of a path PQ. And of course, the end of a path Q is the same as the end of a path PQ. Okay. And when the paths P and Q compose, then chi P times chi Q is just chi PQ. Right. But this is just the same as our Kroneker's delta. It's convenient because I don't have to do the cases when I drag it along. It just understood that if things on the right-hand side of the Kroneker's delta do not make sense, it's never mind because then delta vanishes. Yeah, so just zero. Yep, but now what is that stuff? This is just f of chi pq, right? But then obviously this is the same thing as f of chi p chi q, right? Because chi p chi q is this Kroneker's delta times chi pq. And that's just a number, so I can put it inside. So that's the same calculation as we did before, but I did it again so that you see explicitly I'm not cheating. It's true for absolutely arbitrary graphs. Why on earth anybody assumes that it has to be finite and acyclic to make such a claim? I don't get it. And this is like half of other claims that we have with redundant assumptions. This is completely general. And I think that this is a nice picture. So let me summarize it in the following proposition. So thus, we have proved the following proposition. For any graph E, its path algebra KE is isomorphic with the subalgebra ME of the matrix algebra E0. So here I cannot write the tensor product, but it is a matrix algebra. So we just proved this proposition. And I think it's very nice and neat in itself. And now with the help of the above proposition, now we can prove the proposition that we already discussed before, but even here I tweaked it a little bit. Namely, I realized that for this upper triangular claim, yes, of course, then I need my graph to be finite, that's for sure. But what I don't need is to assume that it's acyclic. What I need to assume is that there are no loops longer than one. So you can have simple loops from one vertex to itself. That's okay. Edge loops are all right. Because I'm perfectly okay with things on the diagonal being more dimensional. It doesn't have to be a field, it can be something more dimensional. And you can have as many loops at a given vertex as you want. The theorem still holds, okay? And you can redo it. So it required a little bit of tweaking, but it is more general. It is more general, and who knows, maybe you will need it one day. And you can always, of course, if there are no loops longer than one, then any acyclic graph satisfies. And when it's acyclic, then things on the diagonal are just one dimension, because the only path from a given vertex to itself is this vertex itself. So it's just one dimension. But you can have as many of them as you want. You can hook a Kunz algebra at every, Hawaiian ring at every vertex, and that's still all right. So let me now write this proposition. So with the help of the above proposition, you can prove the following. And this will be very much like the proposition we had before, but slightly tweaked, as I explained. Okay, so let E be a finite graph with E0 nicely labeled, V1 ... Vn. We need to fix the notation. And instead of saying acyclic, and I say without loops longer than one. that replaces acyclic. So this is somehow in the spirit of Oscar from the previous semester, right? Why do we want to handle acyclic graphs? Well, we can just assume that there are no loops shorter than k, right? So here we assume that there are no loops longer than 1, and you can get away with it. And unlike in the case of Oscar's conjecture, here there is no complication whatsoever. The tweaking is trivial. I mean, you have to go back and redo the proofs because now you have different assumptions, but the arguments are just the same. So again, they're just this natural policy in mathematics. Do your arguments as economically as possible. If you can, in the same fashion, prove something about an extra assumptions, discard them. Okay, don't pay an extra price for something which is just cheaper. Yeah. Okay, but where is the claim? Okay, then it's path algebra KE. Is isomorphic to the upper triangular matrix algebra well, which I denote as UTE of K, and it looks symbolically like this, that I have 0 below the diagonal, and whenever, well, so I have here indices, usual indices I and J, okay, and I have here above the diagonal, and including above and including diagonal, okay, I have chi VI, KE, chi VJ, and this is for I less or equal than J, and for I bigger than J, I have 0. And of course, this is a subset of the full upper triangular matrix algebra, so UTNKE, which by definition is just the tensor product of U, T, and K. So the ordinary upper triangular matrix algebra tensor product with K. So that's like this proposition from the blue book. And but half of its proof is done in complete generality, no assumptions whatsoever. And then I had this other additional loosening of an assumption, namely instead of acyclicity, I assume that there are no loops longer than 1. Okay, so let's see how we prove it. Now the proof is very short because much is done in the proposition that we just proved, the very general one. Okay, so, well, again, we have to recall the proof of a proposition 139 from the previous semester, which actually I should call a theorem because this argument is quite nice and non-trivial. But, okay, let me write it down as I speak. Well, I cannot write proposition 139 on the whiteboard, it would be silly, so let me write, we know from the previous semester that in a finite graph without loops longer than 1, we can always order vertices in such a way totally order, in fact, totally order in such a way that if there is a path from vi to vj, then I is less or equal than j. And this is quite a non-trivial theorem. I call it a proposition, let me rename it a theorem. And this is what I basically had to tweak. So again, I'll ask somebody for the recitation class to prove this proposition 139, but now under these lesser assumptions. So instead of a cyclicity, you'll ask no loops longer than one. Yeah?
I'm confused by this assumption that there are no loops longer than one.
Yes.
So we allow the situation that we have length, a loop of length 1, yes?
Yes.
But doesn't this imply that we can iterate to this edge?
Oh,
If you want something different,
sure.
There are no loops which go
Yes. Yes, yes, you're absolutely right. Thank you, Jacek. That's what I meant. You're absolutely right. Yes, 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 of course. That was very stupid of me. Thank you, Jacek. That's exactly what I mean. Okay, so I will, okay, so let me, maybe I'll do it like this. We will make the following replacement. This is obviously stupid. What I mean is the following, that for any path, P, define V of P to be the set of all vertices in P. And you know what I mean. A path is either a vertex, then it's of course just this vertex, but if a path is composed out of edges, then I take all beginnings of all these edges and all endpoints of all these edges. And this is my set VP, okay? So this is what I define. So I assume the following, that if I have that S of Q is equal to T of Q, so this path is a loop, then this must imply that the set of all vertices in Q is 1. Thank you, Jacek. Of course, that's what I mean. And that's what I use in all the proofs. You're absolutely right. Yep. What I really meant that there are no self-repeating loops longer than 1. Yeah, that's because you can also define the winding number for every loop. And there are no loops of winding number 1 which are longer than 1. So, but you're absolutely right. Instead of winding number, let's just do it like this. So I corrected in the notes. Apologies and thank you, Jacek. This is one of these shortcuts your brain does, and you can make such mistakes. It's obviously a shortcut. That's what I meant. Okay, good. So with this explained, I can now go back to this proof. And as I said, I'm not going to go into it because that's something that belongs to the previous semester. However, the proof is basically the same, just by assumption that there are no loops that have more than one vertex. That's what I should say. All arguments hold. Yeah? But then when I was reading again the proof of this proposition 139, I realized that it's in fact incomplete. I mean, well, it is complete in the sense that the whole argument is correct and sound, but it lacks some explanations. There are some things that are written that are true, but in fact, when you think why they are true, it takes the whole paragraph to justify. So whoever gets this problem for a citation class will have some work to do. But this is a very, very nice theorem, non-trivial and pure combinatorics. But you can tweak it. I checked it. You can tweak it so that this claim that I'm writing here, but you can always totally order vertices in such a way that if there is a path from Vi to Vj, then I is less or equal to j. That still holds. And this is all we need. Okay, this is all we need. Right. So hence, without the loss of generality, we assume such ordering. And remember, when we're defining upper and lower triangular matrices, I told you that that you need more structure. When you look at a matrix, remember, even in linear algebra, when you look at a matrix, it's given with respect to basis elements, to the set which is a basis of the vector space. But a basis of a vector space is a set. It's not an ordered set. So when you write in your algebra class all these matrices that have some order because you write them in this table form, tabular form, that's actually tacitly choosing an order. This is an additional structure. It does not exist in the definition of a matrix. Okay, but typically you in an algebra you work with finite dimensional vector spaces, and since all finite sets can be immediately totally ordered any way you please, you just do such a shortcut. Yeah. But in fact, the matrix is given without an order. And if you want to make sense out of such thing as upper lower triangular, you have to choose an order in your set of indices. And I'm claiming that such an order exists so that my matrix becomes upper triangular. Okay. All right, and so we choose that it has such order, but then we can conclude that then we have chi vi ke chi vj, that's just equal to 0 for I bigger than j. Right, because this is an implication. If I bigger than j, then the space is 0. But this is tantamount to saying if the space on the left is not 0, then I is less or equal than j. Remember the total order. So saying not I bigger than j, it means that I is less or equal than j. That's the total order. Okay, and this is what we just established, right? That an order has this property that if there is a path from Vi to Vj, which means the space is non-zero, then I is less or equal than j. Okay, so now to end the proof. So now the claim follows from the previous proposition. Right, and it is clear because look, what we really need to show is that indeed our path algebra is of this upper triangular form. And then this upper triangular animal is isomorphic to a path algebra. This is what we did in the full generality for absolute n graphs. Okay. Okay, great. So we have 10 minutes left, and I think I'm done with this matrix part. I can now leave it alone. And I have 2 more things to clean up before proceeding with the lecture. One of them is very minor, but Anya is going to use it today. So let me explain it. You see, the advantage of being recorded when you lecture is that then you can more easily spot your own mistakes. And I told you, which is of course correct, and what Anya will use today, is that when I look at my Jacobson radical, so which was given, which was given as the linear span of all chi p's where P is in the Jacobson subset, then I can look at it in a more neat way as the ideal generated by edges so E, of course, is in the Jacobson subset, but is also an edge. But now I take the ideal generated by the chi-E's. And well, in order to see this equality, we referred to a lemma, which was part of this big, of a proof of this big theorem, computing the Jacobson radical for all unit of algebras. So one way, we use the following property of a Jacobson set. I say that FPE times the Jacobson subset, and likewise Jacobson subset times FPE, that this is contained in the Jacobson subset, right? So this is the ideal property. So this implies so let me call it right hand side, and let me call it left hand side. So this property implies what? It implies that the right hand side is contained in the left hand side. Okay, because I'm taking my characteristic function supported by edges in the Jacobson subset, and I multiply left and right, I add them. So yeah, but so what? By this property, which we know from the lemma, I remain in the Jacobson subset. So that's contained in the left-hand side. Sorry, my L looks ugly. Yeah. So this implies that the right-hand side is contained in the left-hand side. But I forgot about the other implication, which is slightly less obvious. Namely, here I use the second property of a lemma, that sort of removing this Jacobson subset from the space gives us a multiplicative subset. So I remove the Jacobson subset from the space of all paths, and when I square it, I'm still inside this set. And this implies that L is contained in R. Why? Well, basically to see that the left-hand side is contained in the right-hand side, I have to see that every path which is not a subpath of a loop contains at least one edge which is not a subpath of a loop. Okay? So all paths and Jacobson subsets are paths of a positive length. Vertices are excluded. Okay? So they're built out of edges. And now suppose that this containment is not true. So suppose that we have a path which is not subpath of a loop, but every edge in this path is I take a path which is not subpath of a loop, and yet it is possible that every edge that I have is a subpath of a loop. Okay. But that's impossible because using this property by induction, you can prove that it's impossible. So why? Because, well, imagine that all these edges that build my path P are not subpaths of the loop. So this means that they are inside the set. So when I compose the two of them, well, I get a path which is not subpath of a loop. Then I add the third edge, I compose, again by this property, I get a path which is not subpath of a loop. So by induction, I can reach finally my path P, which I started from. I see a contradiction. So that's impossible because if I take any finite composition of paths which are not subpaths of a loop, I get a path which is not a subpath of a loop. So this means that if all edges would be not subpaths of a loop, then their composition again would not be a subpath of a loop. So that's how we see this inclusion, right, left to right. I hope I said it correctly, right? So these are, the composition of paths that are subpaths of a loop, arbitrary finite composition will give me a path which is again a subpath of a loop. So if all edges were subpaths of a loop, then the composition in the path would give me a path which is a subpath of a loop. So that's impossible, because the Jacobson radical, Jacobson subset means, the path P is not a subset of a loop. Okay, so this gives the other containment. So this theorem, claims on the theorem, this remark, this observation holds. And I'm wondering how much we can do in 4 minutes, probably not much. So I will not even start these two other things. So what I still want to show you is that the unit of path algebra is the sum of all vertices. And then I want to classify all commutative path algebras. These are simple exercises, but I decided to do them in the lecture because they are part of a very basic structure of path algebras. So I want to do it myself. So maybe let me do the following in the remaining 3 minutes. This is just enough time to do this. I will show you something which I will need for my for what I'm going to talk about in the recitation class. And to this end, it's good to get back to the lecture notes. So I should be able done. Unfortunately, I closed it. So, okay, I have to open it again. You see, some days ago, we had a lecture at our seminar about Leavitt path algebras. So some of you attended, I think, at least Anya for sure, Jacek, I don't remember. No, probably not. But this was a fascinating talk by a top expert about Leavitt path algebras. And he said something which drew my attention, namely how to turn the space of all finite paths into a semigroup. So that's something which I missed. I wasn't aware of it. And I added it here in the elementary remarks. Okay, and this is going to be related to my today's exposition about the convolution rings. Okay, so just look at this. So he used the following trick. Take any graph E and you add the empty path. Right, so I'm not adding the empty set. I'm adding the one element set, which is the empty path. Okay. And now you can globally define multiplication of paths. You see, you don't have a problem. Before I had a problem. If two paths do not compose, then you cannot multiply them. You just say, oh, all right, so chi P, chi Q is 0. But it's at the level of path algebras. How about at the level of graphs themselves? And he said, okay, with the help of this empty path, you can just define the semigroup structure as follows. So if gamma 1 and gamma 2 are actually non-empty paths and they compose, well, then guess what? The result of this semigroup multiplication is just gamma 1 concatenated with gamma 2. But now if they do not compose, I say that the result of a multiplication is the empty path. This is what is 0 on the level of path algebras. And then, of course, if any of these paths, gamma 1, gamma 2 is the empty path, it just multiplies to the empty path. Okay, that's like 0. And you can check that it defines an associative multiplication on gamma which renders it a semigroup. So I don't have a neutral element. That's why it's not a monoid. It's just a semigroup. But this is an associative composition. And but then he said something which seems to me to be false. He said then the Tav algebra is the convolution a ring for this semigroup. And I don't see that it's true. I think it's false, or I don't understand something. But this we will discuss at the recitation class. Let's have this 29-minute break and resume at 11:15. I stop recording. If you have any questions concerning the lecture, please ask them in the recitation class. See you in less than half an hour.